Welcome back. In the last video we have seen the application of Fourier transform to certain partial differential equations, boundary value problems involving partial differential equations. Typical linear equations we have solved with boundary conditions and initial conditions. This video we will see how to apply Fourier sine transform or cosine transform when the problem is boundary value problem is defined over a domain that is a semi-infinite, that is from 0 to infinity. Okay, so we will just start with a problem like this. Solution solve. If you want to solve this equation, this is a heat equation, dou square u by dou t, dou u by dou t, which is equal to that kappa specific heat constant. So you have dou square u by dou x square, and now x belongs to 0 to infinity. So you have a semi-infinite rod which you have 0 to x, that is infinity. Semi-infinite rod you have, it is one dimensional, laterally insulated, so that all the propagation of heat is only one direction, and t positive. So initially at t equal to 0 you should provide, because it is a one derivative, t is time derivative is first order. So you have at u at x t equal to 0, you provide let us say 0. So at 0 its temperature is 0 of this rod, at t equal to 0 temperature of the rod is 0, and then you have this boundary. At this boundary, that is at u at 0, for all times I will maintain 0 temperature. Okay, and then what else you have? So you have a boundary. If you want to apply the Fourier transform here, any Fourier transform, it has to be absolutely integrable function minimum. So you expect, so you are going to apply, since the domain is 0 to infinity, you expect to apply Fourier cosine or sine transform for this u and ux. So you need another boundary condition. So this is the actually initial condition, and these are the boundary conditions. What are the boundary conditions? One is this, other one is simply u and u of xt comma u of xt, u x comma xt should go to 0 as x goes to infinity. So this is so that that means the temperature at infinity can expect in the rod it's going to 0. So this problem we can solve by Fourier. See, once you see this boundary condition, the moment you see the boundary condition as Dirichlet condition, this is the Dirichlet condition. When once you have this three type of boundary conditions, so you have a boundary at the x equal to 0, if u is provided, that is called a Dirichlet boundary condition. Okay, so if your boundary condition is flux condition, that means heat is either going inside or going outside or going inside, let us say, for all time. If you keep that as a boundary condition, mathematically that is u flux means it is going out, so that is a derivative, normal derivative to this boundary at x equal to 0, at x equal to 0 t. This is provided, if this is given. If this is given as a boundary condition, then you should use Fourier sine transform. So such a boundary condition, this is called Neumann condition. First of all, this is called Neumann boundary condition. This is Neumann boundary condition. In this case, we use if such is the boundary condition, we can use Fourier sine transform. You will understand why this is so. Naturally, you are going to use this boundary condition. If you use Fourier sine transform here, I think in this case we use Fourier cosine transform. In this case we use Fourier sine transform, so that naturally we can make use of this boundary condition in the process. So if you are given a Neumann boundary condition, you use this Fourier cosine transform. If you use this Dirichlet condition, we use Fourier sine transform. So let us solve this by Fourier sine transform. We apply Fourier sine transform to x variable. X variable is from 0 to infinity. So, if you do that, you have dou u by dou u, let us use, if you use this derivative dou t of, if you apply for this left hand side, you get Fourier sine transform of u of xi. For this, the time derivative, which is equal to kappa. Now, if you can apply Fourier sine transform, so you have the definition of sine transform is 0 to infinity dou square u by dou x square sine xi x dx. So, if you apply this, you can do the integration by parts, kappa times root 2 by pi, and you have dou u by dou x sine xi x. So, you can easily see this. So, this is the boundary terms you get for this integral when you do the integration by parts, minus what you get is when you get integral 0 to infinity dou u by dou x times derivative of sine xi x, that xi comes out, you have cos xi x dx. So, you want to avoid this boundary condition, you can make them nullify, you can nullify these boundary conditions. If you use cosine transform, you need to provide dou u by dou x, okay, dou u by dou x at infinity or dou u by dou x at 0, okay. Because of sine xi x, at once you put x equal to 0 infinity, this is naturally going to, you do not require this dou u by dou x, okay. So, if you use this at infinity, dou u by dou x, that goes to 0, and if you use this condition, this is 0, and at x equal to 0 sine xi x is 0. So, this together it is nullified. So, you end up getting k xi root 2 by pi 0 to infinity. So, again if you do one more time integration by parts here, so you get u cos xi x, for this you might have this, and minus integral 0 to infinity. So, again cos xi x you are going to differentiate, that becomes sin xi x dx, this is going to be u of x t. So, cos xi x minus the when you differentiate cos xi x, this is going to be minus sin xi x, that minus in the integration by parts minus is going to be plus, okay. So, here now you can use this Dirichlet boundary condition to make this. Now, first of all, this is going to u x t as x goes to infinity 0, when you put x equal to 0, cos xi x is 1, u at 0 t, that is the Dirichlet boundary condition, that makes it 0 here. So, you end up getting finally minus kappa xi square root 2 by pi, root 2 by pi together with this integral, that is simply Fourier sine transform of u of xi, function of xi. So, you need not take it this as 0, you can also use this as some constant, also you can put it if you want keep some constant temperature here. So, let us use some constant C. So, then you end up getting here this will not be 0 here. So, at infinity this is 0, this minus minus plus, what you end up is xi root 2 by pi cos xi x at x equal to 0, it is 1, and u at 0 t, that is C. So, you have, this is what you get, where C is Dirichlet boundary condition. You can do this one also. So, what you end up is this ordinary differential equations, dou u by dou t of f s of u xi plus k root 2 by pi there is no root 2 pi right. So, you have k xi square f s of u of xi equal to root 2 by pi kappa psi c. Okay. So, this is your ordinary differential equation. It is a linear equation for this unknown, this one, this is our unknown, and if you find the general solution, integrating factor, you have to multiply this with integrating e power integral, this is your p dy by dt plus p of t into y of t, which is equal to some given function of, this is just a constant, it does not involve any function of t, so it is just a constant. So integrating factor is if you calculate e power integral kappa xi square, that is a constant dt. So that will give me e power kappa xi square t. So this you try to multiply to the equation. So you see that left hand side will become dou dot t of e power kappa of xi square t times fs of u, which of xi, that is a Fourier sine transform of u, which is function of xi. This is equal to root 2 by pi c k xi times e power kappa xi square t. So if you integrate both sides, you get you end up getting, you integrate both sides. So if you do both sides integration, so what is your time? Time is it's your definition of domain is time derivative. So t, which is positive, you can integrate both sides actually. If you integrate both sides, you end up getting some constant k, let us say some C1, where C1 is integration constant. This is your general solution. So if you do this, this is with respect to dt. So you end up getting e power kappa xi square t times Fourier sine transform is equal to root 2 by pi c kappa xi, and this is divided by k xi square e power kappa xi square t, that is the integration of that, plus C1. So if k goes, xi goes, you end up getting root 2 by pi c by xi, and if you simply multiply both sides, you can end up getting here e power minus k xi square t. Okay, this gets cancelled, this side I have to multiply with this. So this one times plus C1 e power minus kappa xi square t, and this is actually your Fourier sine transform of this. So far we have used only boundary conditions, boundary condition, initial condition as well. So only boundary condition we have used, we have not used this initial condition. So if you use that initial condition, if you want to use that initial condition, so you apply Fourier sine transform to this initial condition. So if you apply the, because this is a variable u at x equal to 0, t equal to 0, x belongs to 0 to infinity. If you apply, you can apply Fourier sine transform there. So since initial condition u x 0 equal to 0, we have by Fourier sine transform u fs of u of xi is also 0. Okay. So xi comma t, this is a function of both xi comma t. So actually throughout, when you apply this, which is function of xi comma, so you also have t. Okay, Fourier sine transform of xi comma t, both the variables. So we have a Fourier sine transform of xi comma t, both. You end up getting xi comma t, and you have this is 0 at t equal to 0. So because I am taking the Fourier sine transform here. So since this is the case, if you apply this here, you end up getting the left hand side 0, this is equal to root 2 by pi c by xi plus c1. So because t equal to 0, exponential quantity is 1. So that makes it c1 equal to minus root 2 by pi c by xi. So you go and substitute there into your solution of u, which is function of xi, which is also function of t. This is equal to root 2 by pi c by xi, c is given constant, plus c1 is minus root 2 by pi c by xi times e power minus kappa xi square t. So, if you remove if take this common root 2 by pi c by xi, this is going to be 1 minus of this. So, this is exactly your so this is t positive and xi is positive because this is Fourier sine transform. So, what is the solution? You just take the inverse transform, taking inverse transform, inverse sine transform, we get to get u of x comma t, this is equal to you end up getting finally root 2 pi. So, you have 2 by pi c by xi, which is a constant, you integrate from 0 to infinity. You have root 2 pi is here, that is become 2 by pi. So, I write it outside, and c is a constant, I write it outside. So, you have 2 by pi c, 2c by pi integral 0 to infinity. This quantity 1 minus e power minus kappa xi square t by xi sine xi x d xi. This is x positive, t positive. So, this is your solution of your differential equation. So, this is your solution of a given problem. So, this is what happens for all times when you keep one end of the rod at temperature C, initial temperature is 0 throughout the rod. For all times, this is what happens. Okay. So, as t goes to infinity, this is becoming 0 sin xi by xi. So, that is going to be pi by 2. So, it's what you end up is finally as t goes to infinity, you can easily see what you can expect u of x t converges to c. That is, you can easily see as t goes to infinity, this quantity is 0 and you end up sin xi x by xi d xi, x is positive. So, that makes it pi by 2 goes, and what you end up is going to be, that is what is expected. So, when you have a rod which is initially at 0 temperature and you keeping a temperature at C here, eventually heat will propagate whatever you are pumping in. So, you are keeping the temperature constant, so that heat diffuses, makes the temperature throughout the rod as C even at infinity. Okay. So, that is what happens. So, this is the solution. So, this is a remark which is on par with the reality. So, the temperature finally is C for all times, for all t positive. Okay. No, for every x positive, this is what is true. Throughout the rod it becomes, it is a rod with temperature, constant temperature C eventually as t goes to infinity, as time passes. This is how we solve if your domain is semi-infinite domain, that is between 0 to infinity. So, let us see another example where this Neumann condition is provided for this heat equation. We will just see that and then we will move on to other type of problems. Let us consider this problem. Solve dou u by dou t equal to kappa dou square u by dou x square. This is a heat equation, one dimensional heat equation for an infinite rod, semi-infinite rod. So, again we consider the same situation as x goes to infinity. This is a semi-infinite rod and you have at x equal to 0, you have provided initial condition. Let me see what is the initial condition. Initially again we keep the rod at 0 temperature. So, u at x comma 0 is 0 for every x belongs to 0 to infinity. Boundary conditions. So, what I do is I try to, so if you use this flux is dou u by dou x here, if I give this as mu, that is actually now outward heat is going outwards, if with mu positive. If I give minus mu with mu positive, is actually you are pumping in some heat. heat is you are pumping in through this surface, some heat is propagating. So, it is passing from outside into this rod constant. So, flux is with this rate it is going, it is coming inside. So, let us see what happens. So, if I write this mathematically, boundary condition is dou u by dou x at 0, x is 0 and t, which is equal to minus mu, let us say. Okay, this is your boundary condition, and if you want to apply the Fourier sine transform or cosine transform, because the domain is 0 to infinity, u at xt and u x x at xt, this is where you are applying the Fourier sine or cosine transform. This has to go to 0 as x goes to infinity. So, these are your boundary conditions. So, you can solve similarly such a boundary value problem for the heat equation. So, we use because this Neumann boundary condition is given. So, we use Fourier, we apply Fourier cosine transform. To u of xt with respect to x variable. To see this, what you end up is dou rho t of, like earlier, fc now Fourier cosine transform of u, which is function of x becomes xi, and this is t. This is equal to kappa times. Now, if I apply both sides, write the definition of the Fourier cosine transform for dou square u by dou x square. This is from 0 to infinity cos xi x dx. Do the integration by parts like earlier. So, you get root 2 by pi, and this, if you do the integration by parts, dou u by dou x cos xi x, for which you apply limits, minus cos xi x, if you differentiate, that is going to be minus sin x, that makes it plus xi 0 to infinity. You have dou u by dou x sin xi x dx. So, since at infinity this is going to be infinity, at x equal to 0 cos xi x is 0, cos 0 is 1, and dou u by dou x at x equal to 0, that is given as your boundary condition. So, you end up kappa root 2 by pi, that is minus mu, but minus plus here. Okay. So, that is mu, and then you have plus xi kappa root 2 by pi. Again, this integral you can again do the integration by parts. So, you see that u and u of x t sin xi x, you apply 0 to infinity limits, and you have minus, and here integral 0 to infinity, one xi comes out because of the differentiation of sin xi x, that makes it cos xi x dx, and this becomes u of x t. So, this is equal to kappa root 2 by pi mu plus this here. If you use the boundary conditions again, u at x t as x goes to infinity, that is 0, and sin xi x at x equal to 0, that is 0. So, this is what happens. So, this is temperature. Assume that temperature at x equal to 0 is finite. So, this is going to be this nullified. You end up getting minus xi square kappa root 2 by pi. So, minus xi square kappa root 2 by pi, this integral together, that is Fourier cosine transform of u, which is function of xi with respect to x variable, which is also function of t, originally u of x t. So, x becomes xi, another variable as it is. So, your partial differential equation becomes ordinary differential equation like this. So, dou t of linear equation here, like earlier, f of u of xi comma t plus xi square t, xi square kappa f Fourier cosine transform of u of function of xi comma t, which is kappa mu root 2 by pi, just a constant. So, what is its solution? Solution is f of u of xi comma t I multiply e power integral, this is your p, xi square, if you do the integration here, xi square kappa t, multiplication with respect to dou dot t, I multiplied. So, this is what it, if I multiply this factor throughout, so you have kappa mu root 2 by pi e power xi square kappa t. So, this is what happens. So, if you multiply this factor both sides, left hand side is this. So, you can do the integration with respect to t, do the integration with respect to t plus some constant c, where c is arbitrary, c is integration constant. This is for t positive, okay. C positive and xi is also positive. So, this integration and this derivative goes, so you end up getting f c of u of xi comma t, which is equal to kappa mu root 2 by pi is a constant, and this if you do the integration, you have kappa xi square e power xi square kappa t, that is the integration, plus c times. So, you have when you have this quantity here e power xi square kappa t, this is what it becomes. So, this makes it, finally if I write u of xi comma t, this is root 2 by pi kappa mu, and this gets cancelled. So, you have to write here e power minus xi square t kappa t. So, this divided by kk goes, mu kk goes, you end up getting mu by xi square, and here plus c by c times e power minus xi square kappa t. So, again if you use we have not so far used initial condition, that is this. If you apply the initial condition, which is 0, we kept the rod at 0 temperature, since u of x comma 0, initial temperature 0, you have u f c of u, which is function of xi at t equal to 0, this is also 0, okay. We get this. So, if you apply this to here, so left hand side is 0, right hand side 2 by pi mu by xi square, and this becomes c. So, c is minus of that. So, that implies f c of u xi t, this is c is minus of that. So, you that is common. So, 2 by pi mu by xi square comes out, which is minus, and c is minus of this, minus of e power minus xi square kappa t, for t positive, xi positive. So, you are left with simply taking the inverse transform, taking inverse Fourier cosine transform to get the required solution. You get the solution, that is u of x comma t, that is if you do the definition of the inverse transform, another root 2 pi, that is 2 by pi, mu is constant, comes out, and what you end up is 0 to infinity for this function 1 minus e power minus xi square kappa t divided by xi square cos xi x d xi. This is for x positive and t positive. So, this is exactly your solution. So, you can calculate this integral as t goes to infinity. So, again like earlier, you can also have this remark, as t goes to infinity, what happens to this u of x t, as you pump in this thing. So, you end up getting 2 by pi times mu integral 0 to infinity cos xi x by xi square d xi. This integral So, you have to evaluate, and if you see you keep pumping, you end up getting some if you constantly do it as t goes to infinity. So, you end up getting temperature, it is infinity. I think this quantity we really do not know exactly. So, if you evaluate, we know. So, what you expect is this as t goes to infinity or temperature, this is true for every x positive. Throughout this is what happens. At x equal to 0, cos xi x is 1 by xi square is minus 1 by xi, and then that is 0 to infinity. So, that is infinity, right. So, that is expected. I think this is going to be infinity. So, this integral is not convergent integral. So, as you expect is going to be infinity, cos xi x by xi x square. If you fix x, I think it is going to be infinity. So, this quantity, so that is what is expected, because you have a rod, you keep on pumping some heat inside. What happens to the rod eventually? Eventually you will see that is going to be u has to go to infinity. Thus clearly you can see at x equal to 0 1 by xi square. So, whose integration is 1 by xi, if you substitute the limits, this at xi equal to 0, that is going to be infinity. And similarly at any x positive there may be, so that we do not know. So, if it is convergent integral, we can just do this as in how do we evaluate for all x positive, x equal to 0, that is infinity here, and then x positive you can rewrite, this is the even function inside, minus infinity to infinity cos xi x by xi square d xi, this is half of that. So, your integral is half of this. This you can do the contour integration. Yeah, so clearly, so this is you have 1 by xi square 1 by xi square, and at 0 you have this is not convergent integral, it is not the usual sense. Okay. So, that is what is expected. So, you can easily see as you pump in the heat, is eventually the temperature of the rod becoming more and more, it will become bigger and bigger. Okay. The temperature just increases eventually to infinity throughout the rod. Okay. That is what you can see from this example. If you are given initial condition as some other things, or the boundary condition as something else, we cannot use anything. For example, dou u by dou x plus some h of some constant times u, which is 0. For example, if this is a mixed condition or Robin condition, they say Robin boundary condition, we really do not know how to solve this. Okay. We may have to use, we cannot solve by these methods, we may have to use some other methods. Okay. That is a different issue. So, we will not solve this by this method if it is Robin condition. So, this is how we solve this heat equation of a semi infinite rod. So, let me also solve some Laplace equation. So, let me solve one more problem using this Fourier cosine transforms. Let me consider a Laplace equation in a semi infinite domain. Let us say if this is your x, this is your y. So, this is a quarter plane problem. If your domain is this one, x positive, y positive, x positive and y positive. So, we will solve this, solve dou square u by dou x square. So, this is what is your, assume that this is your plate, same quarter plane plate, and which is in a steady state. So, temperature of this at steady state, dou square u by dou x square and dou square u by dou y square equal to 0. This is x positive, that means x is between 0 to infinity, y is also between 0 to infinity. What is your boundary? This is your boundary. So, that is y equal to 0, this is x equal to 0. So, I just need to give the boundary conditions. So, what are the boundary conditions you provide? U at x equal to 0, that is 0 y throughout y, for all y let me give some constant c, and then u at x 0, y equal to 0, along here I keep this temperature 0. Okay. I maintain constant temperature here, I maintain 0 temperature here, is already in the steady state. Okay. In order to apply the Fourier transforms, I at infinity gradient of u that goes to 0 as r as x square plus y square goes to infinity. Now, any direction if you go to infinity, a gradient change in the temperature goes to 0. Okay. So, such is the problem. The solution you can apply same technique by Fourier sine transform we apply, because we have the boundary conditions are Dirichlet. So, we apply Fourier sine transform to x. X if you apply Fourier, so boundary condition is this. Okay. If I apply Fourier transform to the x variable, boundary condition is at x equal to 0. So, which is Dirichlet. So, that implies we have to use Fourier sine transform. Use Fourier sine transform to get what you get is fs of u, which is function of xi comma y. Okay. No, so this is yeah, xi comma y, for which dou square by dou y square, this is for this, plus if you apply for this root 2 by pi integral 0 to infinity dou square u by dou x square times sin xi x dx, which is equal to 0. So, this is what it becomes. So, first one dou square y by dou y square of fs of u, which is function of xi comma y, plus root 2 by pi. So, do the integration by parts again. So, like earlier dou x sin xi x from 0 to infinity minus into xi times cos xi x dou u by dou x 0 to infinity, which is equal to 0. So, if you do this implies dou square fs of u function of xi y by dou y square. This one plus what happens to these boundary conditions, dou u by dou x, dou u by dou x at x, this is a u of x y, u of x y, this is u comma x y, we are doing at x equal to 0 to infinity. So, what happens to dou u by dou x because of this, what is this one? So, at x equal to 0, this because of sin xi x, that is 0. What happens to dou u by dou x at x goes to infinity? If I use this one, because this gradient, the temperature is gradient, which is not which is going to be 0. So, at infinity, if you maintain a C temperature, you can expect a temperature as t goes to infinity, or when in the steady state, what you expect is the temperature here will be there throughout the plate, same temperature. That is why we do not say u goes to 0 as x square plus y square goes to infinity. In that case, C is inconsistent, C has to be, that means you are keeping 0 temperature here, temperature C here, and you expect this to be in the steady state. That means throughout, so it's eventually it has to, there is a temperature gradient, so C and this side, so linearly it distributes to up to infinity, right, that is in the steady state. So, anyway, so we just take this way, so gradient is gradient of u goes to 0 as x, that means dou u by dou x, dou u by dou y, that makes it this 0. So, this contribution will not be there. So, you get root 2 by pi xi times, again if you do the integration by parts, you get up end up getting u of x t cos xi x minus another xi comes here, xi, that is because of derivative of sine, cosine, that makes it minus sin xi x, that makes it this plus, and you have u of x t, u of x y, sin xi x dx, okay, equal to 0. So, again, so here you have to apply the boundary conditions at x equal to 0 to infinity. So, this implies dou square by dou y square of fs of u xi y minus, again here, so this goes to at infinity, at infinity again this so you can say that at infinity this is also goes to 0, the temperature goes to 0. So, if you apply, you see that this is also 0, you need this u of x t at infinity has to be 0. So, even if this is C throughout at infinity, so C linearly distributes finally, so that it is in the steady state, that is what you expected. So, if you have a semi finite rod which is temperature at 0 and L linearly between 0 to L, so you have a linear function between 0 to L maintained. So, in the same way that is the steady state condition. So, that it does not depend on that does not depend on t. So, the same way in the 2 dimensional plate you have the similar situation. So, to this goes to 0 and you have a cos x equal to 0 t, that is this is not t, this is y, u x comma y. So, x comma u at 0 comma y, that is also c. So, you have a c minus plus root 2 by pi xi c, okay. And then this becomes minus root 2 by pi, this integral will become Fourier sine transform. So, you have xi square Fourier sine transform of u of xi comma y equal to 0. So, this if you write it outside, minus this is equal to root 2 by pi minus root 2 by pi xi c. Okay. So, you can write dou square by dou y square of f s of u xi of y minus, this is your ordinary differential equation. So, you can simply integrate to get the general solution. So, what is the general solution? F s of u comma xi y is equal to, so if you see this is the second order equation, you have if you write e power y k type of solution, if you look for what you get up is k square minus xi square equal to 0. So, homogeneous solution, if you look for this one, you get k equal to plus or minus xi. So, you have e power plus or minus xi y into C1 plus C2 times e power xi y minus xi y. These are the two linearly independent solutions for this homogeneous equation, and plus particular solution, and you can see that particular solution will be minus both. So, you can see that this is going to be 2 by pi c by xi is your particular solution of this equation. You can easily calculate by methods in the differential equation. So, by looking at this you can easily see that this is the constant, that is 0 here. If you put it here in the place of this, f s of u xi y is this place, you end up that both are same. So, is actually satisfying this particular solution. So, you have a general solution is C1 C2 are arbitrary constants, and this is your solution, xi positive, y is positive. So, still we have not used, again like earlier we have not used this initial condition. What is the initial condition? Not other boundary condition we have not used, that is u at x equal to 0, right, u at y equal to 0. So, if you use this, you can see that Fourier sine transform of u, since you can write this, since u at x 0 is equal to 0, we have Fourier sine transform of u at xi comma 0 is also 0. So, if you substitute here, you have left hand side is 0, right hand side C1. Okay, another condition is as y goes to infinity, this this Fourier transform also should go to 0. Okay, u of x comma y goes to infinity, goes to 0 as x goes to as y goes to infinity. So, if this is the case, if you look at this, if you take the Fourier transform for this f s of u of xi comma y, this also should go to 0 as y goes to infinity. Okay. So, because of this I can see that this C1 has to be 0. Okay. So, that means f s of u of xi comma y is actually equal to C2 times e power minus xi y plus root 2 by pi c by xi. This is what is my solution. So, now if you since the other boundary condition you have this, if you apply here, if you apply the boundary condition here, the left hand side, that is 0, right hand side is C2 y equal to 0, this is 1 plus root 2 by pi c by xi. So, that makes it C is minus of that, C2 is minus of that, that makes it f s of u of xi y is root 2 by pi c by xi is 1 minus e power minus xi y. Okay. So, this is what it is the case. So, you take the inverse transform, inverse and inversion gives finally u of x y equal to 2 by pi and c comes out integral 0 to infinity 1 minus e power minus xi y divided by xi sine transform, we have used sine xi x d xi. This is what is true. So, you have because you can split this into two integrals, sine xi x by x positive and xi positive. So, because x positive, you have sine xi x by xi d xi, that is going to be pi by 2. So, you have c, first one is c, the other integral is 2 by pi c, 2 c by pi integral 0 to infinity e power minus xi y sine xi x by xi d xi. Okay. This is what exactly u of x y as I positive and x positive. So, what happens to this? How do I evaluate this integral? So, you can do some simple technique. So, let me start with this integral. So, let me, if I start this simply, if I start since I know, since 0 to infinity e power minus xi y times sine xi x d xi. What is this one? This is actually equal to x divided by xi square plus y square. X divided by x square plus y square, that is what you should have. Okay. Since this is the case, since this integral we can simply by integration by parts you can find this. Because of this, what I do for this, I will try to integrate with respect to y, I integrate with respect to y. So, integrate this because y is also positive, integrate with respect to y from y to infinity. If you let me apply, to get, what you get is integral 0 to infinity integral y to infinity e power minus xi y dy sine xi x d xi is equal to x comes out y to infinity 1 by x square plus y square dy. So, what is this one? This is actually equal to integral 0 to infinity. If you do this, divide by minus e power minus xi y by xi sine xi x, okay. And if you apply this to y equal to y to infinity, y equal to infinity d xi equal to x if you cancel here. So, y to infinity x you take it out, you have 1 by x and 1 plus y by x whole square. So, dy by x. So, that you can 1 by x you can put it inside, that is actually equal to tan inverse y by x. Now, we put y equal to y to infinity. So, if you do the tan inverse infinity is pi by 2, tan inverse infinity minus tan inverse 1, that is tan inverse y equal to y. So, you have y by x. Okay. And the left hand side it becomes 0 to infinity, and this is infinity, it is 0, and minus plus this is going to be e power minus xi y sin xi x by xi d xi. So, if you, because this is also, you can rewrite this as tan inverse x by y. Okay. So, this is from trigonometric inequalities, you can get it. So, finally, you can easily see that this this solution is u of x y equal to c minus, if you do this one, is integration 2c by pi times tan inverse x by y. So, this is what it happens for x positive, y positive. So, this is your solution. This is the required solution for your problem. Okay. So, this is how you can apply your Fourier cosine or Fourier sine transform for any of these problems, either steady state heat equation or for one dimensional heat equation. These kind of problems in semi infinite domains, or when you see one of the domains x domain or y domain, when it is a semi infinite domain, that is 0 to infinity, you can apply Fourier sine transform or cosine transform and solve the bound value problems. So, with this we end the applications of Fourier transforms, and so you can also, I will give you an assignment some of the problems similar to this what I have solved. In the next video we will introduce the Laplace transform from the Fourier integral theorem. Start with the Fourier integral theorem. So, that is valid for an absolutely integrable function, and from which we define what is we pick up from which we pick up what is called the functions that are exponential order, and then we derive we just modify this Fourier integral theorem, and what we end up is getting some kind of form that defines Fourier Laplace transform and its inverse transform for an exponential order functions. Okay. This is what we will see in the next video. Thank you very much.